Yeah. All right, so we're still talking about Taylor series. And today we talked about series which are not continuable beyond the circle of convergence. So today we're going to end on positive note. We're going to talk about series that are continuable. So, and the question is, if you have a Taylor series and radius of convergence, let's say, is 1, it doesn't matter which is, and suppose you know something about the coefficients, something good about the coefficients. So suppose an are values at the non-negative integers, g is some nice function. So what can we say about continuation of f beyond the unit disk? All right, and well, the example, governing example to start with, for instance, if g is a constant, let's say 1, so we have geometric series, and that continues to the whole extended complex plane except 1.1. All right. Now, a little bit more general. So this is a theorem of Leau. And Fabry a little bit later. If g is a polynomial, of degree m, and then f of z extends to the whole complex plane except one point, and has a pole of order one higher than the degree at 1. And what's interesting, converse also holds. That's less straightforward part of the theorem. What does it mean? It means if you have a function, Taylor series, radius of convergence 1, which actually the function, not the series, extends to the whole plane except point 1, where it has a pole of given order, then the coefficients are values of a certain polynomial of degree 1 less at the integers. Okay. Let me just give you one push to how this theorem is proved, especially converse, sort of starting point. For the converse, it's is an entire function. Under this condition, and then it's hard work. All right, another theorem, a little bit more advanced, also Leau, same year, and it's actually part of the same paper, and Fabry. If g of z is an entire function of there are various classical names, order 0, minimal order, I'll tell in a moment what it means. Both terms are not good, actually, intuitively, because they don't really explain what they mean. It means for every epsilon, the lim sup r goes to infinity of g r e theta is finite. That it's less or equal than 1, it doesn't matter. It's finite. So it, if you've never seen it, this it's an entire function, obviously, because cosine has only even degrees, and it's of order less than 1. I said, yeah, 1/2. All right. So.
Sorry, is the constant that you're comparing to the order? So if you had c there, it would be less or equal to c.
Yeah, the major thing is that it's not 1. It's less than 1, strictly less than 1. What order certainly matters when you study entire functions, but in this context, order. Yeah. Order entire function, it's how does it compare with the exponential? Okay. And then the conclusion is, so this is.
I think they're asking, you have to put a constant in there, right? If you said order C or something.
Yeah.
There would be a constant.
Yeah, if I ignore this limit, it just means that starting with some r, when you go to infinity, it grows not faster than any exponential of the first order. but cosine square root of z is of order exactly 1/2. I mean. Okay? Okay, so if you have all this, so your Taylor coefficients are values of such a function at integers. Then f of z continues analytically to again. And again, the proof is the starting point is the same. You look at this function, you notice that it's an entire function, and then it's 2 pages of calculation. It's not a trivial theorem. Okay. And moreover, the converse is true as well. Okay, what in this context, what does it mean? It means that if you have a function with Taylor series, radius of convergence 1, which extends to the whole plane except 1 point, 1. Then if it has essential, so there is an isolated singularity, and as we do in basic complex analysis, isolated singularity can be of 2, 3 actually kinds. Removable singularity, so it's not a singularity, essential singularity, and a pole. So there are 2 possibilities. If it's a pole, we're back here, and that means that function of 0 order is actually a polynomial of degree 1 less than order of the pole. And if it's essential singularity, it's a function, entire function of minimal order. Okay. All right, now enough of what other people did. What actually happened, the paper is a page and a half. It says a remark on a paper of Tao Chen. What happened 33 years ago, Tao Chen came to Arkansas, gave a colloquium talk, and I went home and wrote that paper. And I never looked into his paper. They appeared in the same volume, but I did last week. And actually, I have no idea what he proved and if he proved it. And this is no disrespect, but it's certainly a different. He claims similar result, but I'm not sure. It's 18 pages, and the technique makes me a little bit suspicious. It's harmonic analysis, singular integrals, and whatever. And now you will see why I'm a little bit suspicious. So this is the theorem. So if f of z is an z to the n, an is equal to g of n, and g is a bounded, and I'll say a few words about that. It's just to give you an idea, because the proof doesn't change for much more general statement. Analytic function. This is, what year is this? 1997. It wasn't before Leau and Fabry. Analytic function in a sector S phi, which is Z argument of Z less than phi less than pi over 2. Okay, I'll draw the picture in a moment. Then by the way, I don't have to say anything about radius of convergence because it's automatic, it's 1. It's obvious from just take the limit. So then f of z is analytic in the unit disk. That's Cauchy-Adamar. And extends to a heart-shaped domain. And of course, I should have, by now, in 33 years, I should have put it in Mathematica and have a sketch, but I didn't. You're everybody welcome to do this. And I call it G phi, which is transcendental. Z is R I theta, such that 2 pi minus cotangent of phi times log of R greater than theta greater than cotangent phi log R. Okay. So we start with the unit disk, and then have you ever seen such a domain? You should be impressed. Comes out all the time, right? It's something, this is 0.1, and it's something like this. This point you can calculate e to the minus of cotangent phi. If you want to see sort of the dynamics of it, well, I'm sure you can see it in 2 seconds if you put it in Mathematica or whatever, but I don't think Mathematica was available. It's not that it would make any difference, but if this is phi 1 and this is sort of increasing, this is phi 2 bigger than phi 1. So what happens when phi hits pi over 2? Any guesses? Well, that's a little bit too much because it's going this way and then that way. G pi over 2, which is the union. It becomes. I still can't.
Self-intersecting.
No. Not that I know of, but that's as much as I know about it. I don't think so. All right. Couple of remarks. I don't have converse, and I don't know what converse should be. And of course, I should have put the sector. That's where coefficients, kind of the function which determines the coefficients, lives. So remark.
Does that mean that that's the exact domain of extension?
That's exactly what I don't know.
That's what you don't know.
Yeah. I know this. That's for sure, because that can be obtained by. I won't have time to talk about Adamar multiplication of singularities. This most beautiful theorem on this subject, but it follows that you can get from half plane. There is Adamar multiplication of singularities. There is a theorem of Leau and Lindelof for the half plane when the function is in the half plane. So I know that this is sharp. That's what's in my mind.
What G? The constant G.
Oh, polynomial. That's a remark. Yeah, I said bounded. Well, bounded is obvious, right? Bounded is bounded function in the sector. I mean.
They could be defined all, not necessarily only.
Well, if they're defined, let me write down the remark, and you'll see the answer, I think, to your question. So the statement and the proof extend to G having polynomial growth. Instead of being bounded in the sector, it grows like not faster than some power, or minimal order, but in the sector, or minimal order. It's terrible terminology, but it's in this sector. This is sector. Okay. Now, that's what I want to say. Moreover, if G is even of exponential growth, in the right half plane, plane. And that means, so, G, yeah, of order, how did I say it? Of order theta strictly less than pi. Okay, let me try to write down what I mean by that. G of rho e to the I psi, whatever, is less than e to the theta plus epsilon times rho, and psi is between pi over 2 and negative pi over 2. So G is analytic in the right half plane, and it grows, it can grow exponentially, but strictly less than pi. That means theta strictly less than pi, so you can always squeeze in epsilon. Yeah, if you say of order theta, yeah. But the major thing is it's less than pi, strictly less than pi, the order. Okay, then with all this, then f of z extends, which is, I remind you, g of n, z to the n, extends to the sector on theta less than psi less than 2 pi minus theta. All right, so in this case, we have, this is the origin, this is the half plane, where coefficients are values of the function in the right half plane, which has this growth. And then the function is a priori analytic in the unit disk, but actually what happens with this, it goes which way it goes, unless for some reason I have a blank here. Yeah, I see something I drew wrong. Positive real axis and what's near it is always off limits. It's it goes to the left from that sector.
In your original theorem, you don't have, so that's kind of your pi over 2.
Yeah, that's not.
Kind of your pi over 2.
Yeah. The point I am bringing it in because in my original theorem, very original, I lift up the proof from that theorem, which is which is, it's,
What is it that you said about the G pi over 2 domain?
G
I
pi.
don't understand what you said about it being extreme. You don't know the exact domain of analyticity.
No, for G pi over 2, I know.
So you're saying if
Just hold on, let me just write the name. 1902, and Lindelof. Uh, 1900. Obviously different dates, but totally independent. So what's the question?
So my question is, if you have your fixed phi less than pi over 2, you know that it extends for sure,
To the cardioid. Well,
but you don't know if it extends more,
right.
right?
I don't.
Okay.
But for pi over 2, it's sharp.
Huh?
For pi over 2, it's sharp.
For pi over 2 is sharp, yeah.
So
Because there are examples already here.
so in other words, if it's bounded in the whole, whatever, right half plane, then that G pi over 2 is sharp. That's what you're saying.
If it's, yeah,
If the, right?
yeah. And there are examples because this is basically this theorem for pi over 2.
Well, wait, what for the G pi over, what happens when G is just a constant? Little g is just a constant. And then
Well,
Well,
then
it's
it's
more, but
then it's geometric series.
But
But what I'm saying
the
is-
G has restricted growth, right? In that,
I guess the question is, what happens, what are the limits in case of G pi over 2 on that segment 1, 2, 3? Right, like so, how can that be sharp? Or maybe I'm just not understanding how it can be sharp if you can do better than that G pi over 2 when G is a constant.
Well,
well, the restriction on.
it's a good question, what is sharp?
No, but G is only required to be bounded in the sector. So if it's.
Bounded
if it's a
or
constant, it's
that
bounded
restriction on order, that makes no difference
Sharp,
between.
that would be a good G to use for sharpness.
I see, okay, I see. So it's not that any function that satisfies this, that
Right.
it, you can
No,
never
no,
take
obviously,
any.
because the other
Right.
theorem already
Yeah.
has a
Right,
strong
right, okay.
growth.
Okay, yeah.
Like, could you
Yeah,
find a
yeah.
G that's only has that growth in that
Right,
region,
right.
and then what's the biggest
Okay.
domain?
Yeah, and I always thought that you can, but I'm just not to bother with such an unimportant question. But I don't know how to do it. I mean, the obvious way how to do it is to start with a bounded function for which the boundary of the sector is a natural boundary.
And what is that function?
Right. Right. And then a good question, and then what? And because you know, there are all the theorems about natural boundary go one direction. If something bad happens to the coefficients, if something bad happens, then it's the boundary of the domain is a natural boundary. You can't extend anywhere else. There is no really any good results except those.
Yeah, it feels like once you have some sort of control over the growth of the function, you throw out that.
Yeah, but you see how simple this converse is, because these are the only converse statements I know, but the singularity is 1 point. What do you mean?
Take the limit from half to half plane. That's 2 for your function x. Because you can extend it everywhere except for the cut. Right? You cut the segment.
Well, if I take a bounded function in the right half plane, then I get the whole plane minus the array from 1 to infinity. Which limit of what?
Like vertically, you mean?
What do you mean vertically?
Like the
It
limit
means
is
if you
y
take
goes
the
to
limit of
infinity.
your function that's extended down to where it hits the cut.
Uh,
What happens?
Good question. I mean, if I have time, the way to, I don't know, I mean, a priori, but the way to study it, there is this Adamar of multiplication. That's exactly what Adamar multiplication of singularities theorem is about, which deals with when you have two power series and you do with fixed radii of convergence, and you do the stupidest thing on Earth, you multiply corresponding coefficients and say pray and see what happens. And that's why when you do with matrices, it sort of then traveled into matrices. Sometimes it's called Schur product of matrices. It's sort of freshman dream, right? You take all elements, multiply them through. It's very often called Adamar product because of that. And Adamar proved, actually I think it's the same place where he proved Cauchy Adamar. He proved that singularities, sort of, you go on a ray beyond circle of convergence. At some point you hit the singularity. For one power series and for the other power series. And then for this stupid product, the singularities will be a subset of all the products of singularities. It's a very simple theorem, very often misinterpreted, in particular that, like Bieberbach in his book, Analytic Continuation, he dedicates twice as many pages discussing how silly people misinterpret that theorem than to prove the theorem. Because it's not true that all the singularities are obtained that way. But the singularities you get from the product of two power series is a subset of the possible. And I won't have time. But if you are interested, there is a paper where I actually wrote it in the notes, but that Fredholm first paper, which I talked about last time, where Fredholm made a mistake. So one way to prove it is to push idea of Fredholm correctly with the PDE, getting the additional. But the other way to prove it is with the Adamar multiplication of singularities theorem, but it's kind of a couple of tricks, and it's in our paper with Harold Schipper. Okay, let me at least indicate how, I mean, because how does one do this? And as I said, I don't claim invention of the method, because all these people, I would have invented them if, weren't for them before, 100 years before that. All right, so okay, I should probably return here, right? If I write here, how does it? It's fine. Okay. You said it's fine. So sketch of the idea. You take the partial sum. Well, you get rid of the constant, okay? 0, because 0 is not the point in any sector, in any nothing, and the zero term is a constant term. So whatever the continuation goes of all other terms, the zero term you can slap in. So the partial sum equals, okay, I have this picture, integral over circuit gamma, which I'll describe in a moment. Okay, what is the circuit gamma? A priori, the circuit gamma is any, this is up to n, any circuit which surrounds the first n integers. I mean, when you see it, it's like, of course, it's a residue theorem. It's nothing else. But until I actually saw it, I wouldn't have guessed it. It's just beautiful. It's totally how the residue theorem works. Okay. Do we agree that this is true by residue calculus? Any questions on that? Because there are only, this is, by the way, analytic. I mean, you take the branch of the logarithm, but this is e to the z, which is fixed, log w, and everywhere where you're operating in the right half plane, there is no problem with logarithm. Okay. Yeah?
So is that W or N? Is Z to the W?
Z to the W, yeah. This is you have a problem with that? No, I'm just kidding. No. And there are only single poles, right? Okay, then there is a homework problem. Unfortunately, it's yeah. Well, unfortunately, if you look in my paper, there are two references. Dini's book, which is 700 pages something, reference go to the page 33. And Alfred's book, Complex Analysis, it's also 34, 33. But this is the ansatz for all W in the whole complex plane subtracted the countable union of the circles Z such that Z minus n less than eta, where eta sufficiently small. Okay, the denominator is bounded below. Is greater or equal than there are no more zeros. I mean, okay. It requires a little argument, though. I mean, it's, yeah. Any complex analyst can do it. All right. Now, what actually gamma we take? We take specific gamma. Let's see if I can find another. All right. You take, did I say 1/2 or? Okay, take any point alpha here, and okay, the only thing I want, alpha is less than 1/2, and it doesn't really matter. Okay, and then take the sector of the same size. So this is 2 phi. And then you cut it so you separate first n points in this formula by a circle. All right, so this is our gamma we're going to work with. All right. Now, here's the gist. I mean, it's the last seminar, so running over time. Whoever is interested can read the paper. Although, I must say, Catherine is a witness to this. After 34 years looking at this paper, I was mightily shaken that maybe it's not true, but then finally it turned out to be true. So what you do, you start evaluating for specific z on the negative, like as far as possible from the action. I mean, if you know something about that function for that specific z, it coincides with your function, and that function automatically is going to continue to where it says is going to continue, you're done. All right, so that's the first thing. And now you split the contour into two parts. One is obvious. What did I call it? No, sorry. The circular part. This is the radius. I mean, I said n plus 1/2, but it doesn't matter. It just has to be strictly between n and n plus 1. And then you have the integrals over two rays, well, closed rays. So all right. Now let me just say a few things about how the estimates go without boring everybody. on the circular part, the denominator is because of this observation. It requires a trick, but a little trick. Direct calculation doesn't work. But you get that this is bounded away from 0. Now, in the numerator, it's greater or equal if you want for W is equal to alpha plus R e to the I theta, then denominator is going to be greater than C, the same C, times e to the pi R, absolute value of sine theta. And that is certainly bounded away from 0 uniformly, no problem. There is a little argument you need to do for the absolute value, because one is obvious, and one you have to play a little bit with algebra, which I don't want to do now.
I'm confused about your estimate here. Where is W?
W is on the circle, on the part of the circle.
On gamma R.
Yeah.
Is that miscast and plus a half?
Below.
It's bounded below uniformly. Well, it's bounded below uniformly because that C comes from this observation. But actually, it's a little bit more.
And my point is you just need absolute values.
Well, the absolute value you are playing. Okay, here's the hint. But I'm not going to. Denominator. Now don't say because I'm writing it. Don't say I see either. Okay, so for theta positive, one works. For theta negative, the other works. And that's how you get. The point is, you have to need absolute, you need absolute value. You need, otherwise you get exponential decay for denominator. It's not good. Numerator, so let's see. That's why I took the easy road with bounded function. Numerator. Is, well, divided by denominator. So is less or equal. Here we have a constant, and here we have bound on G. Then when you do calculation, and remember that absolute value of exponential is exponential of the real part. And earlier formula that e to the I theta is cosine theta plus I sine theta, and I is the square root of -1. And you also have to figure in the length of that thing, which is, it's a sector of radius 2 phi, so it's r times 2 phi. All right. And then e to the alpha plus r cosine phi. And here comes the savior, log of little r. Little r is the absolute value of z. That's why we took z on the negative radius. Because what do we have here? Phi is between minus pi over 2 and pi over 2. This is negative, and this has exponential decay. So that goes to 0. So eventually, when you sum the whole series, there is nothing left from the integral on the curved linear part of the contour. And now, okay. So our f of z, for z is equal to minus r, f of z, we agree, you better agree, is over the side length of the angle, g of w, zw, dw, and e to the 2 pi I w minus 1. All right. And then let me just write two estimates about what happens with the denominator. So e to the 2 pi I w minus 1. Well, first is obvious. It's e to the 2 pi I w minus 1. Triangle inequality. But it depends on which side. The estimate depends on which side you are. That's why you have two sides for the argument of z. One is e to the 2 pi r sine phi minus 1, and that is when argument z minus alpha is negative phi. The other is 1 minus e to the minus 2 pi r sine phi, and that's on the other side. All right. So that's denominator. Now, on each one, you want to compare it with the estimate of the numerator. Now, the point is that certainly g, that's we're talking, I mean, if you throw in minimal type, then you have to put this epsilon, and but in the way it's stated, g doesn't matter because it's bounded. But what happens is the following. There are two possibilities. When you calculate the absolute values and blah, 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 cosine phi log of absolute value of z plus r sine phi minus argument of z. E to this power and divided by e to the 2 pi r sine phi minus 1, and that is on the lower part. And the last formula I'm going to write is e to the r cosine, I put e in the wrong place, e to the r cosine phi log absolute value of z minus r sine phi argument of z and divided by e to the 2 pi r sine phi minus 1. And this is for argument z minus alpha is phi. All right, well, that's what you have. And the point is that you have to have both sides decay exponentially. So you need no, it's actually correct. It's correct now, right? Okay. No. 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 It's actually was correct. Yeah, the first time around. And well, no, it's not, because you have this estimate with exponential for the denominator. It's not suspicious at all. Oh, for God's sakes. Okay, well, I have the paper on my phone, so.
Well, no, we can talk about that.
Well, this is the paper where you don't talk. You calculate.
What makes you suspicious of this?
It doesn't.
Being able to be tackled by
It doesn't. I just want, you know, when you are standing there, it's actually correct both times, because okay, sine phi minus 1, and here is well, half of the time. 1 minus e to the minus 2 pi r sine phi. Let me check again. Yeah. All right, and okay. For some reason, I'm writing it wrong. It's plus times argument, and correct. And the second one is exponential of this r cosine sine phi argument of z, and divided by this. Now it's correct. And the point is, let's just check. Both should go exponentially to 0 when r goes to infinity. So
First one, though, you have an exponential of, so you have the ratio. Is the exponential of the denominator of the ratio or the exponential of the higher ratio?
it's exponential of numerator, actually. Yeah. That seems okay?
Yeah, that's good.
All right. So what do we have to have exponential decay? And I think it's easier to start with 2, because when r goes to infinity, that disappears, and r cancels out. It just, and what you have to have, that this expression, well, times r, is negative. And that exactly tells you that argument of z is larger than cotangent of phi times logarithm of absolute value of z. And here is the other inequality. All right, well, that's too bad.